You made it in? You got through the big line? Okay. My name is Chris Carter. Welcome to the Bankhead Theater. I work here. I'm the development director of the Livermore Valley Performing Arts Center. We are a nonprofit cultural arts organization in Livermore. Who's here for the first time at the Bankhead? If you could raise your hand. Anybody? Oh, great. Well, welcome. I hope you come back. We do lots of great things throughout the year. And we are a mission-based organization. Education is very important to us, especially education in the arts. And we have a very strong belief, especially here in Livermore, that art and science and technology are all can work together in a really great way. And that's why we're doing this here today. And we're so glad to have you here. I first want to thank our sponsors for this fair. This is free to the community because we have generous supporters. TopCon, Land Research, Lawrence Livermore National Laboratory, Majestic Net, Draft Space, Black Lab R&D, Cisco Systems, Sandia National Labs, School Retooled, Tri-Valley Coder Dojo, Livermore School District, Livermore Science and Society Center, the Independent Newspaper, Google, and Castlight. So thank you to our sponsors. And I want to encourage you to check out everything. There's over 50 booths here today. There's a lot of great things to look at and learn. And we have some great speakers today. Just a reminder, make sure you know where the exits are before our speaker starts. And also for the upcoming speakers, I just want to let you know you can't take your seats. You go out and you come back in. But I want you to come back and I want you to go out and I want you to check everything out here today. And now I'm going to introduce our speaker, Pierre Graube. And Peter, I was talking to him earlier, and I asked him what motivated him to go into this career. And he said when he was in 4th grade, he was reading about neutrons and protons and things like that. And his teacher asked, what did he want to be when he grew up? And he said, I want to learn the nature of reality as a 4th grader. That's pretty cool. Peter has worked at NASA for more than 30 years on automated wind tunnels, a specialized wind tunnel test, arc jets, centrifuges, laser systems, and a shock tube, a rocket motor test bed. He recently engineered a software specification procedure to comply with stringent new software standards. Peter brought to NASA extensive innovation experience. After earning a degree in physics from the University of Michigan, Peter taught mathematics for a year at St. Paul's School. Then he moved into engineering, where he discovered a passion for machine automation and went on to automate factories for automobiles, mirrors, furniture, and brass extrusions. An avid orienteer, Peter has competed in 24-hour events in the Arctic Circle and Central Australia. Please welcome Peter Graube.
Well, good morning. Isn't technology amazing? In the sense that we live in an amazing age where robots are coming of age, and it's really a remarkable transformation that we're seeing. I've heard that it's actually being compared to like 12,000 years ago in the transition of humanity from hunter-gathering to sedentary lives on the farm. So anyway, I have been working at NASA for roughly 30 years, and did you know that there's many NASA centers throughout the United States? One that you might know of is Kennedy Space Center in Florida. Another one might be Johnson Space Center in Texas. Well, there is a NASA center also here in the Silicon Valley. At the southern tip of the San Francisco Bay is NASA Ames Research Center. So this is about a quarter shot of the entire complex, and I'm not going to go into the details because we don't have enough time. But just in this shot here, you can see the world's largest flight simulator here. They do airplane development in this hangar. Over here they do biological research. Over here they develop space capsules. And then notice these funny structures sort of scattered throughout. These are called wind tunnels. So what is a wind tunnel? Well, it's used for research on airplanes. So if you have an airplane flying through the air, or the airplane is staying still and the wind is blowing over it, the effects are much the same. There's really not much difference. So why would you want to have the airplane standing still rather than moving? Well, if you want to do research on it, and let's say you want to research how it behaves when it's at such and such a pitch angle. Well, in the real world, if you try doing this, the airplane's going to go in other directions and not stay at that particular position. Whereas in a wind tunnel, you can actually make it stay in that position. So here's a shot of a model airplane inside of a test section. The model itself is attached to a model support through a mechanism called a sting. So we'll be talking more about stings later today. So getting back to this picture here, we're going to be looking at this monster in the center. This is called the Unitary Planned Wind Tunnel Complex. It's actually 3 wind tunnels in one. That is why it's called the Unitary Wind Tunnel Complex. There's 4 gigantic motors here in the center. If you connect the motors up to this side, you can drive wind around this circuit here at 2.5 times the speed of sound. So the speed of sound typically you'll refer to as Mach. So Mach 1 would be 1 times the speed of sound. The air goes around this circuit at Mach 2.5, and the test section is in this building right here. So if you go around this circuit instead, the test section in this area can go up to Mach 3.5. If you attach the motors to the other side, this particular wind tunnel only goes up to Mach 1.5, but that wind tunnel specializes in the transition from subsonic to supersonic flight. There's all sorts of instabilities, and that's what you really want to research if you're going to be going supersonic. And that's why this particular tunnel is heavily used. So we're only going to be looking at this side, and if I refer to it as the 11-foot tunnel, that's basically the dimensions of the test section. It's 11 feet wide and 11 feet tall. So let's now look at the, let's go to the next slide here. This is a schematic of the entire complex. And again, we're only looking at the 11-foot transonic wind tunnel. There's the 4 drive motors here. There's a compressor here that drives the wind. So there's a single shaft connecting the 4 motors, and they drive the 3-stage compressor. The wind then goes round and round like this, and then in the test section is where you do the testing on the models. So we're going to now take a closer look at the drive motors. This is a single motor. It's 65,000 horsepower. It weighs 154 tons. And so with 4 motors in place, that's them now having been put in place, that's a total shaft power of 260,000 horses. I was responsible for automating those motors, and it was quite the feeling to ride a herd over 260,000 horses. So, here's some more statistics about the motor. There was an upgrade in 1998. That's the upgrade that I just mentioned. We worked on it. So primary voltage of 7,200 volts, primary amps of 4,500 amps, and so on. So, and also the full load speed, it can go up to 695 rounds per minute. And so when you're driving the compressor that we'll be looking at shortly, that's basically what those motors are used for. Oops. Okay, so going back to the schematic, we're now going to look at the compressor here. Whoa, I went way back. What's going on? Oh, I see. Okay, never mind. Okay, I have to get used to it. I'm of the old school. Electronics sometimes confuse me. So anyway, here we are, back to the schematic. And so we're going to be looking at the compressor. This is 3-stage compressor. And this is a schematic of that compressor. So the air now is coming around a corner at this point. Notice the shaft now is coming from the motors from the right-hand side, and it drives 3 rotors or wheels. Each one of these wheels is 17 feet in diameter. There's bearings here. There's oil pumps and vibration sensors and temperature sensors. Lots of things that go inside of this teardrop shape. So the teardrop shape itself doesn't have the air going through it, but the air goes around. You see these little channels all around the teardrop shape? That's where the air goes, and that's where the blades, the propeller blades, are located. So this is a shot of the compressor. It's been opened up for maintenance. Here's some people doing maintenance on it. Each rotor has 52 aluminum alloy blades. Each of the rotors is forged steel. Each rotor with the blades weighs 160 tons, and at 685 RPM, that's rounds per minute, it moves 6,250,000 cubic feet per minute of air. Or, another way to put it is 400 tons of air per minute. So, now let's go forward. That was the test section, or I'm sorry, the compressor. Now we're going to go to the test section over here. And these are models inside of the test section. We'll recognize that as the shuttle. Now that's been retired. And then various airplane forms. Sometimes they shine laser light through the windows, and then they can trust that there's some little particles of dust that are flying through, and from those dust particles they can get the reflections, and with using Doppler effects figure out the velocity of air around the model. The model itself is pretty much packed full of instrumentation. What you see here is it won't duplicate all of the internals of the normal airliners in this case, but it's full of wires and things. So, and those wires then go through the sting back to the data systems of the wind tunnel. So here is a model, and then here's the type of pictures that you can get off of the model. This is called a Schlieren type of picture. Again, it uses lasers, and you can see the various streamlines coming off the nose and other places. So for scientists, that means a lot, and that you can use those sort of studies to optimize the airplane design. So that's another model. This is what is called a semi-span model. It's much bigger, but you lose some flexibility in being able to move it around. But larger models like this actually have greater fidelity to real life. So that's what you really want to do. So that is the Unitary planned wind tunnel complex. Now we're going to switch gears here for a minute. Not only do wind tunnels test airplanes, they also test rockets. And so this is one of the first rockets that NASA launched into space. That's the Mercury capsule right here. Now notice at the nose of the Mercury capsule, there's a little tiny rocket. That is what is called an abort rocket. So suppose that the main rocket starts to catch on fire and it's ready to explode, and it's going to perhaps kill the astronauts in the capsule. So what the designers wanted to do is have this little rocket carry away the capsule from the exploding main stack, and therefore save the astronauts. So here's some more pictures. Here's the Apollo that went to the moon. There is its abort rocket. And here's the new generation of space capsule being developed by NASA. It's called Orion. That's the capsule there. And the abort rocket is actually clipped off from the picture, but you can see it's pretty large because that's the largest capsule ever developed. Here is the abort rocket being worked upon. So you can see it's pretty massive just by itself. So I would like to play a video clip.
At the White Sands Missile Range in Las Cruces, New Mexico, engineers and technicians are preparing for a very special test. The Launch Abort System is a sophisticated new rocket tower designed to pull a spacecraft away from danger on the pad and during initial ascent. For the first time, all the components of the system will work together. The test not only develops core technology needed for future spacecraft, but also directly improves the chances of crew survival in an emergency. The name of the test is Pad Abort 1. It's the mid-1960s, and the Apollo program is testing its launch escape system. At the White Sands Missile Range, a squatty rocket nicknamed Little Joe 2 launches an Apollo capsule for a high-altitude test. Engineers want to see if the escape system can pull the capsule away from danger in the event of emergency. The unmanned test shows the escape system works. Years later, an escape system was used for real on a Russian Soyuz rocket. When spilled fuel caught fire on the launch pad, an escape rocket pulled the capsule away from the hazard, saving the crew members' lives. For the Pad Abort 1 test, engineers will utilize the Launch Abort system to lift a mock Orion crew module. The test simulates an emergency situation not unlike the Soyuz incident, where the spacecraft is still sitting on the launch pad. The Launch Abort system builds upon knowledge of the past and applies modern technology and new innovations to make a more capable means of escape for the crew. This technology can be utilized to make any spacecraft safer for human space exploration.
Actually, if you look at Mercury, Gemini, and Apollo, they all had a launch abort capability in different ways. For these capsule-like designs, there's a way to pull it away from the booster and save the crew. So it takes that fundamental idea, but our current launch abort system is actually much better than those systems. With the thrust, with the attitude control system that we have on it, we can actually get the crew away from the vast majority of even very unlikely contingencies we can imagine.
3 newly developed motors will work together on the Launch Abort system to create a new level of control and stability during flight. The abort motor is the most powerful and begins the escape process.
Well, it's pretty amazing. The abort motor is the biggest motor that lifts everything up. It's got about 500,000 pounds of thrust, and it's going to get the whole vehicle up off the ground to achieving about a Mach 0.6 in about 3 seconds.
Tested in Utah, the abort motor utilizes a new style of propulsion that saves space and weight while still achieving remarkable power.
Where our booster is bigger, so what we decided to do rather than sit it on top of a lattice structure was actually turn it upside down so that the thrust goes up and then turns out on the nozzle, so we have a reverse thrust nozzle. So that's a new technology that we developed for this. It makes it shorter than we might otherwise need to be, which is good for mass and other things.
While the abort motor initially pulls the spacecraft from danger, an attitude control motor provides a new level of steering capability to orient the spacecraft.
We have an attitude control motor which has 8 thrusters or pintle valves. So it's a solid rocket motor, single solid rocket motor with 8 valves. These valves can individually be varied to vary the thrust at 8 different locations around the circumference of the top of the abort motor. It's more stable. It gets you in a better attitude when it's time to deploy the parachute, so we can get the crew module into a much better and more stable position. It also allows us to reduce the weight, the overall weight of the launch abort system.
With the spacecraft safely away from the danger and properly positioned to deploy parachutes, a third motor, the jettison motor, ejects the entire launch abort system tower, leaving the crew module to fly by itself. A forward bay cover is ejected and parachutes deploy for a touchdown. Pad Abort 1 gives engineers a chance to see how the fully integrated launch abort system works under flight conditions. The build-up to this test has utilized the diverse talents of NASA centers commercial industry, and even the military.
Okay, and then there's one other video. This one doesn't have any sound to it. But these are live shots, and these shots show you in slow motion what's actually happening during the abort process. If you noticed, one of the speakers mentioned that the abort motor accelerates the capsule from 0 to Mach 0.6 in 3 seconds. So that is 400 miles an hour in 3 seconds. Notice how the entire capsule is covered in flames. It's really, really loud. It's not only hot, it's also loud. And that's what we'll be talking about more. You see, those astronauts in there are subjected to a lot of noise, and you get enough noise going, and you could actually kill the astronauts. We don't want to do that. So in order to design the spacecraft a little bit better, here's a still shot of what you're just seeing now. They decided that they needed to do a test in a wind tunnel of the abort motor with the capsule. And so they chose for the wind tunnel test. Let me just back up a little bit. Notice when this rocket is being launched here, this is a satellite carrying rocket. It does not have the abort motor at the tip. But notice all of this cloud. And that cloud actually comes from water being pumped into the pit that's underneath the launch pad. Because if you, when you introduce water, the water absorbs the sound and mitigates the heat. And otherwise, if you don't have the water, literally the concrete and the launch pad would be pulverized. It would be turned into dust. So by using water, it absorbs the vibrations from the noise and the heat. And all of this that you see here is steam, believe it or not. Okay. So here's the launch again. Notice in the abort process, you don't have water quenching the heat nor the noise. And also, you're literally in the flames themselves, so it's very, very loud. So they decided they need a test, and they decided to use the 11-foot tunnel at the Unitary Planned Wind Tunnel Complex. There's a model. It's a 6% model. These are 2 astronauts coming to visit during the test itself because they were very interested in what the results of the test would show. Here's the master model maker. You can imagine there's a lot of instrumentation within the model, and yet the efflux volume, basically the exhaust from the rocket, is washing over a lot of the model, and you have to have dissimilar metals. And those dissimilar metals, it takes a lot to work with them. And he's the man that figured it out. Then this guy over here is the local genius that figured out what kind of fluid to actually use as the simulant for the exhaust of the rocket. Notice he's showing the NASA administrator here. That's Charlie Bolden back in 2010. And there's shots here of the Orion spacecraft being washed with the exhaust of the abort motor in the wind tunnel. And so this guy thought deeply about it, because you can't really use a real rocket there. It will contaminate the tunnel. And also we wanted to do 200 plus tests. And you can't be like switching out rocket motors for each test. So how do you do it? Well, the genius here figured out to use helium. And not just helium, it's hot helium, pressurized hot helium. So the temperatures that were anticipated for the test were 700 degrees Fahrenheit, or that's 370 degrees Celsius. So here's the reasoning for why use hot helium. And the relevant parameters are the speed of sound, velocity, and density. So there's other types of considerations that we won't go too much into detail there. So here is a schematic of the system we set up. Now mind you, we had 19 months from the start of the project to the 1 week window of time of use of the wind tunnel, because the wind tunnel is very precious, its time. And so we were assigned a 1 week slot, and so we have 19 months to prepare for it. So we figured out this particular layout. Over here, there are helium trailers and accumulators. Then there's some valves, and ultimately the helium goes into this heater. It's a 5 megawatt heater. Then it goes into a pipe that's also being heated with electricity. And then by the time it gets to the floor of the wind tunnel, it then penetrates the floor of the test section and goes into the sting. And that then leads to the model itself over here. We don't show that here. So this is a shot of the trailers. There's lots of helium. We literally had helium trucks lined up coming to deliver. So there's one helium truck, let's say, loading up the trailer. And if you notice back here, there's another helium truck. If it's empty, it's going to be pulling out so a fresh truck can pull in, because we literally had a sort of a assembly line going. So these are the accumulators for the helium. Over here, again, you see the trucks, the helium accumulators, and here's the heater for the helium. It's 5 megawatts. And from here, the hot helium penetrates the building and goes to the test section. Here's the piping leading to the test section. Notice this U joint here. Basically, when the pipe starts heating up, it expands. And if you don't allow it to expand, it will break or break pipe supports, and basically you'll have a mess on your hands. So lots of smart people designed the system. Then it penetrates the floor, goes up through these, I'm not sure why they use two, to go into the sting. That's where the hot helium would go, into the sting. Here's another shot of the hot helium ducts going to the sting, and then the sting provides the model with the hot helium that then goes to the nozzles over here. Now, the model itself is very complex. I mentioned that it's full of sensors. In this case, it's full of pressure sensors that are very sensitized. They're called coolites. I'm not sure where the word comes from. But anyway, it's full of these sensors, and here's a shot of the model being assembled. You can see the guts of it. Look at all those wires, and there's sensors all throughout the interior of the model. That's a little cleaner. The model has now been installed. There's still a lot of cabling hanging out, waiting to be landed. And then finally, when everything is said and done, here's a clean shot of the model all assembled. The data and power, whatever electrical power you might need on board, comes through this, cable collection. And normally it would go through the sting, but the sting in this case has been dedicated to just ducting the hot helium to the model. So, going back to this schematic here, notice these little arrows coming off the instrumentation. These arrows go to a control computer. It's called a programmable controller. Programmable controllers are wonderful machines. They basically never crash. They are deterministic. That's in contrast, let's say, to Java, where Java is non-deterministic. Programmable controllers can be programmed to be entirely deterministic. So that's the real advantage in control systems. So here's a schematic of wires that go to a card that ultimately leads to the programmable controller's brains. There's a lot of different types of activities that needed to be done within the 19 months leading up to the 1 week test period. So you have to strategize about, let's say, different modes of operation. You needed what's called model cavity cool down. won't go into detail, but you have to integrate the tunnel data system, the heater controls, and other controls in the tunnel. You have to select devices, safety analyses, signal conversion, sensor mounting, wiring diagrams, which you're seeing right here. The configuration of these input cards is done similarly for output cards. The heater configuration, and you have to have lots of people working, and you have to sort of try to help them along, manage them. So even after all this work, you still don't know what to put into the brain. And this is my specialty here. I've started developing these logic diagrams. There was something in a primitive state back in 1980 when I started working on them. And I just took what was already there and multiplied it by about 10,000. So for this particular test, I developed about 100 sheets of logic like this. And this logic then is able to be translated directly into the code of the programmable controller. So there's a one-to-one relationship. You'll notice over here there's like 3 buttons to turn on the heater, and then this actually tells the system that the heater has been turned on. Another thing that had to be developed is an operator interface. So this is where all of the switches and objects are being shown. And the particular switches that I showed in the logic diagram in the previous slide are this little cluster right here. So when it's actually in operation, a lot of the switches go away simply because they're not visible. We make them invisible because otherwise it clutters up and confuses the operator. You only want to show the operator what needs to be seen. In this particular case, notice that the heater is red, and that means that it's on. Here's a shot of one of my assistants actually monitoring the system. So, a little bit of drama in working up to that 1 week period of tunnel time where we actually performed the test. We had big changes to the delivery strategy after month 9, so all of previous logic had to be tossed out and we had to start afresh. The heater itself, when it was being installed, was dropped in month 16, and we were able to still gracefully recover from that. So the test was begun in early September 2010, and we tried to do the first shot and nothing happened. And we realized, oops, whoever did the simulation did not do a good job. They had us use a particular strategy, and it turned out that strategy was not viable. And here we were in the first day of a 1 week test window, and the system was not working. Okay, so what to do? And so here we got together, we strategized, a lot of smart people, and we figured it out. So here is a shot of what is called a strip chart recording. The green line here shows you the signal going to a valve that would modulate how much helium is getting into the piping going to the model. The set point for the pressure of the helium is the red line here. The reason it's going up on the slope rather than just a step from 0 up to its ultimate set point is that if you just simply open up the valve, there's a front of high pressure helium that would make its way through the piping, and it would damage the model. So you have to build the pressure up gradually using a ramp. And so that's what you're seeing here, is the ramp coming up here, and this is where it levels out, and the acceptable, what we call swim lanes, are between here and here. And what you want, if you can see the yellow line here, you want that line to be in between those two extremes. And notice that it nicely settles in to the red line. This is what is called ringing. And in this particular case, the ringing was within acceptability. So anyway, the green line is the set point to the valve. The valve position itself is chasing the set point. And then the yellow line illustrates the feedback of the pressure of the hot helium that is chasing the red line. So after about another 3 shots that day, we actually solved that problem, figured out an alternate strategy, got the computer programmed, and we still have to tune it up for the new strategy, and we got it going after another 3 shots. So the 4th shot actually was successful. And this is what is considered to be a successful shot here. So we were very pleased. We actually met all of the 200 test runs that we were supposed to be doing. This is one of the Schlieren shots of the flow coming out of the nozzles of the abort rocket, washing over the Orion spacecraft. From data like this, plus of course all of the internal pressure sensors that are feeding their signals back to the data system to the right, through the, well, not through the sting, but wrapped around the sting, you get pictures like this. And using pictures like this now, you can optimize the soundproofing inside of the capsule, because you don't want to use a whole lot of soundproofing, let's say, for areas like this. You want to use a lot of it maybe for areas of like this, where there is a lot of sound. And that optimizes how much cargo can be carried in the Orion spacecraft. So this is all part of the design process. Oops. Okay. So this is the group in the control room. That's the project manager. Actually, he's the local in Livermore. He's the genius that figured out the hot helium. She is one of the test managers. Here's the other test manager. Here's one of my assistants. There's me. And that's Charlie Bolden, administrator of NASA. And that's the entire crew, the designers, the electricians, a lot of people that didn't get to sit in the control room, but they all helped with the project. So it was a successful project, and it was part of NASA Ames Research Center, just about an hour's drive from here, all a part of NASA. So thank you for your attention.
Okay, don't go yet. Before you leave, Peter, I just want to present you with this from the Livermore Innovation Fair. This is a plaque recognizing your work and for coming here. And I hope you like flowers. Thank you very much, Pierre. He's going to be around. He's doing some interactive sessions in the green room back here. Do you know when is that?
12:15 is the first session.
At 12:15. So if you want to work with them personally and see some really cool instruments, you can go talk to Peter right here down this hallway at 12:15. And at 12:45 we have Jack McCauley coming, the creator of Guitar Hero, founder of Oculus Rift. So please come back at 12:45 for Jack McCauley. Thank you. We'll see you in a few minutes.